Let's jump into writing code to describe memory arrays. But before we jump into writing HDL code, let's talk a little bit about key aspects whenever we design memory. So some of the key aspects is the depth, basically how many rows, and you are going to see me using addr_width to specify how many bits an address should be, and I'll make it as a parameter so our code is scalable, so you can actually specify the size of the memory as much as you want whenever you instantiate an instance of it. Also, the other key aspects is the depth, the width, and the data width is going to be another parameter that will describe basically how many bits is a word, basically the width of a word. Of course, we're going to have to specify the number of ports and the direction of the ports. So for example, in this here, you're going to see that I have 1, 2, and 3 ports. They're colored differently so that we can easily visualize it. 2 of these ports, which is the red and the green, are read ports, and the blue ports is actually a write port. So that's specified with the direction of the port. So synchronicity of a port access, whether you access it with a clock or at any time, this is not very clear on the graph, and as a designer you're going to have to make a decision when you should read or write synchronicity of a port. Generally speaking, a write is always synchronous. That's how I've seen it. The read is up to you whether you want it asynchronous or synchronous. Asynchronous meaning you can read it all the time. You don't have to wait for the clock to come over or the active edge of the clock, whether that's negative or positive. The other thing you're going to have to decide whenever you write code is simultaneous address access. Basically, if you're reading 2 at the same time, which is not a big deal, but whenever you're actually writing and reading to the same address, that might be a big deal, and you're going to have to talk about it. All right, so let's jump into coding. I'll show you how to write HDL code to describe memory arrays by showing you how to write a code for memory array of 2 ports, and that memory array has a read port in here, the one in red, and we have one here in blue, which is the write port. And usually now we know that how many ports we have and the directions of the ports. So we have one dedicated read and one dedicated write. The read, I'm going to consider it to be an asynchronous read, and the other one, which is the write, should be a synchronous write. So I started this file in here, which I called RAM2port to describe this particular memory array. And as I suggested before, I'll be using parameters to describe the address width and the data width. So by default, I'm given the address width, which is actually just how many bits each one of the addresses are. So for example, I have an R address and a read address, or like read address is the R address and the write address, which is W address in here. So they're address width and another address width. So I said that by default, I'm going to consider them 3. So 2 to the power of 3 is 8. So technically, if I don't change them, I'll have 8 rows in that memory area I'm about to write. And the data width, which is the width for the data bits or the data ports. So this is a read data, this is the write data. You're going to see that. So data width in here and data width in here. And of course, they're written inside here, the address width and the data width. So I decided by default to make it an 8-bit. That means it's a single byte. These again can be changed when you instantiate a RAM2port. And I started by specifying the different signals that we need. For example, of course, we need a clock in here. And let me just highlight these. So for example, the write address, so I have a write enable in here. Okay, so that's the one. And then of course I have a write address and a read data or write data here. And in red in here, what I have is I have the R data, this one here. This is the R address, sorry, and then I have the R data, the one in here, which is an output. And as you can see, the only output we have is this particular R data in here. Everything else is just an input. All right, so how do we go about writing code for memory array? Well, here's how we do it. We usually start by saying, okay, I need a register. It's a register file or a memory array. And that register file, like we usually do, like with data, it has to be of data with -1 all the way to 0, and then I will just call it memory. Not very original, but it indicates whatever it is that we want. You can call it whatever you want in here: RAM, ROM, memory 1, memory 2. If you have several memories, the name is yours. Kind of like what we did with any other register or signal, kind of like what you see in here. So the least significant bit will be 0, and the most significant bit will have this particular index in this particular case, because width is 8, so it goes from 0 to 7. Now, the way we can do this and make it a memory is by specifying another dimension. So you can think of memory as a two-dimensional array. It is not, but you can think about it this way. Okay, and the way we do it is we say, okay, we need 0, and we need it to go to all the way to 2 to the power address width minus 1. And that's how we make it a memory. So one comment before I move forward. So you will see that here I use the same convention that I've been using, which is 0 all the way to data width minus 1. So the least significant bit will have a 0. But here it's a little bit different. And the reason why it's different, it's because I will start it's not the least significant bit anymore. It's actually the first row and the last row. And convention tells me that it has to be in the flipped direction. So the 0 in here will have, this is the first row, okay, and then here it's actually the last row in here, which says 2 to the power of address width. It's complaining because it needs a d in here. Address 2 to the power address width minus 1, and as you probably know by now, whenever we're talking about parameter, address width is 3. This will be replaced by 3. 2 to the power 3 would be 8. 8 minus 1 will be 7. So this will go from 0 all the way to 7. I'll get 7 rows in here. All right, so now this is how we define memory. Technically, I am done describing this particular memory array. What I need to do is I need to start with the ports, okay, depending on how many ports we have. In this particular in this particular example, I have 2 ports. So what I will do is I will say, okay, let's do the write port in here, or the write operation, sometimes I call it. Okay, and the way we do it is, well, we decided that it has to be, according to the description that I have in here, the write port has to be synchronous. Because it has to be synchronous, it has to be associated with a clock. So I'm going to have to say always at the positive edge of the clock. I will do begin and an end. And the way we do it is we say if write enable. Well, what we need to do is we need to make sure that the memory at address write address, because we're doing a write operation here, and because we are writing in a sequential circuit in here, this has to be an unblocking assignment. It has to be write data. Okay, and that's how we go about writing the write port. This is the whole thing about the write port. Of course, I probably have a typo in here, so let me just do this here. All right, and this in here, and there you go. All right, so that's the write operation. And now, because I need the read operation to be asynchronous, as you can see in here, that means it has to be outside the always statement, because it doesn't depend on the clock. It's always readable. So all you have to do is just tell me assign our data to be equal to memory at read address, and we're done. That's how we describe a memory array. And again, this could be of any size, any size you want, and this is how easy it is. All right, so let's see if I actually do open the RTL analysis, what would I get? Well, the RTL analysis told me you're trying to write RTL RAM, and that's exactly what I was trying to write. All of these are the inputs, and of course the R data is the only output. Now, if I want to see what really happened, basically what type of resources did we use from the RTX 7, I have to go to the implementation. Usually this is closed by default, and we're going to have to run the implementation and see some sort of reports, some utilization reports. So let me run this and come back after it's done. So the implementation is done now. You will see here a very short design run like report that tells me the lookup tables. It only used 8 lookup tables. There's no flip-flops, and actually it didn't use the BRAM. And if you actually open the implementation and you want to get a little bit more details, you can open the implementation, and we go in here. There's a utilization report somewhere in here. Of course, we can take a look at the timing, but nothing is happening in there because I'm not using that in any circuit, and my constraint file is actually not complete because I'm not connecting all the inputs and outputs. But anyway, if I want to just see the report utilization, for example, so that we can see what happens, and you can see in the hierarchy, it tells me, well, you use slice lookup tables as memory. That's how it used it. And you can actually take a look at it, and you see what the slice logic is. It used it lookup table or lookup tables as distributed RAM. So technically interpreted as a distributed RAM, the one that I'm not interested in using, but it just used it because it is available. That's why Vivado used it. Let's take a look at another example of a 3-port memory array, and in this particular case I will use 2 read ports, and these are the one in red and green in here, and I'm going to consider them as asynchronous read ports. That means the data here is available regardless of the clock, and it will have one synchronous write, the one you see here in blue. As you might expect, the code should be very, very similar to the 2-port version. So what I did is I created a new module. I called it RAM 3 ports, and I defined all the signals, the clock, the write enable. Really what I did is I took the RAM 2 ports, and all I had to do is just replicate the address for the read and call 1011, and of course the same thing goes with the data. All right, so because as you can expect, the code is going to be very, very similar, so I'm going to copy the code from the original 2-port version. I'm just going to copy it and put it in here, and let's see what happens. Well, how do we define memory? And it's exactly the same way, because we wrote it as parameters. It's exactly the same way. Well, the write port, basically in the ports, I need to actually specify the 3 different ports: the first one, the second one, and the third one. So in here I have one write port, and that write port didn't change. It's exactly the same. However, the read port is a little bit different now, or not different, it's just replicated. I need 2 of them. One is actually 0, and the other one is 1 in here, and of course the data, the address is has to be changed as well, and we are done. That's basically how we describe a 2-port, or actually 3 ports, 2 read and 1 write address. Of course, the read addresses are asynchronous, so you can actually go and see the implementation and the implementation here, run it and see the utilization report and whatnot. But more interestingly, what if I decided that maybe this green one in here, I want it to be, let's say this one has to be synchronous. I don't want it to be asynchronous. Well, the solution is pretty straightforward. If I need the data, read data 1, or the first read port, or the one with number 1 to be synchronous, all I have to do is just cut this one from here and put it within the always statement. That's all you need to do. And of course, we're going to have to remove this assign, and there you go. We're kind of done. And the reason why I said that we're kind of done is because you're assigning something to our data. Of course, this has to be in an unblocking assignment, because this is actually a synchronous design in here. So you have to use an unblocking assignment. And of course, it's still complaining because you're assigning something to a data, so you're going to have to define it as register in here. And at this point now, you have a 3-port RAM that has 2 synchronous ports, 1 write and 1 read, and 1 asynchronous read in here. And if we take a look at the schematic just to see like how different it is and how it actually implements it, we will see this particular diagram in here, and you can take a look at it. Really, it's almost exactly the same, except for one of the read port is passed through some sort of a register. So this is the synchronous port in here. All right, let's take a look at the implementation here. I'm going to run the implementation to see. Well, as you might expect, we didn't use the BRAM at all. It used the 8 flip-flop. I think that they are this register in here and 16 lookup tables to implement this HDL here. And you can go to the report utilization in here so that you can see breakdown of everything you used. And we'll take a look at it here. All right, so we can say okay. All right, so the utilization report is telling me, well, you are using this many lookups as distributed RAM, and you can think about it like this is how many flip-flops, or you can take a look at the summary and it will look and it will give you everything. So the utilization you have in terms of lookups, you have 16, and they are used as RAM. And of course, this is the number of available versions. This is for distributed RAM, and really your utilization is 0.08%. It's a really small one because by default we have it like, I believe, 8 rows by like 8 bits each, and then I have a flip-flop of 8 flip-flop.